Now my speech is about optimization of the process parameters for the manufacturing of open cells iron foams with high energy absorption. I come from the University of Rome Pro Vergata, and with my colleague Professor Tata and Professor Dobiba from the University of Tokyo, we present these results. So just a definition of what is a metal foam. A foam is a cellular structure of solid metal in which some gases are entrapped inside the foam support. So what is usually a defect in this case gives us some properties particulars. Foams can be of many kinds, can be closed cells or open cells, so can be connected between them or not. And if we look on the surface, we can find closed cell foam on the left with the surface smooth of the metal, and typical application, a structural application for this kind of foam. And on the other side, on the right side, the open cell foam, in which some pores are interconnected from the surface to the core, mainly employed for functional applications. Main properties of metal foams: high specific toughness, optimal energy absorption during deformation in compressive test, high damping coefficient, and fire resistance for aluminum foam, but at the same time also good welding properties. For all these reasons, main application fields are in transportation, automotive, naval aerospace, in which lightness is important for the structure, but also in filtering, biomedical applications, or in thermotechnics. Some problems are still open in the foam manufacturing. First of all, the production process control and the repeatability of the process. So, dealing with an unstable phase of molten metal, the porosity control must be enhanced in order to take under control the porosity dimension, the porosity shape and size. It's quite difficult to obtain complex and big shape, but at the same time we have also high cost. In this work we focus the attention on the optimization of the process parameters for the production of open cells iron foams with high energy absorption. We manufactured 4 kinds of foams with a ratio 60-40, 50-50, 46 and 30-70 urea iron foam. We perform mechanical tests on this foam, and we analyze the energy and the energy density ratios in different kinds of iron foams. To do this, we started from the sintering and dissolution process, in which, starting from the base metal that are iron powder about 70 micrometers of diameter, plus the addition of a filler agent, the urea, 2 millimeters of average diameter, these two components are mixed together, compacted, in order to obtain a precursor, which is put inside boiling water in order to remove urea, to obtain the foam, but to obtain mechanical properties. Other way is important to sinter the metal. So the final phase is sintering. After this phase, we obtain the metal foams. First troubles we find during this. It was not possible to obtain a uniform urea distribution inside the precursor due to the difference in geometry and in the density between iron and between urea. So to perform better distribution of urea inside the precursor, it has been necessary to employ a binder. So we used acetone while mixing iron and urea, and after this step we obtain a uniform porosity distribution of the precursor, not like in this case. So boiling water 100 degrees C for 10 minutes, and sintering temperature and time 950 degrees C for 30 minutes. Scanning the range of the composition, iron and urea, we found just 4 ratio of foamability range, so 60, 40, 50, 50, 46 and 30, 70. This was the lower limit of formability of the mixture. Sample 20 iron and 80 urea was not able to bear the treatment in boiling water, so it's not possible to obtain a foam with satisfying properties this way. These are 4 kind of sample which have been subjected to compressive test. Compression test, an MTS inside machine, 50 kN maximum load, 2 mm per minute per set speed, 5 Hz acquisition frequency. On the bottom right, the typical stress strain curve, compression curve of metal foam after a small linear elastic step. There is a big plateau up to 40–50% of strain with a low level of stress, and finally there is the densification while no pores are no more inside the foam. So for what concerns the deformation energy, in the left I reported some results. The red curve is relative to foam 60–40, and on the second, the blue to 50–50, the violet to 40–60, and the green to 30–70. In order to make a comparison, we set a deformation up to 35% strain fixed, and we calculated the energy absorbed, the specific energy absorbed up to that deformation in order to have a comparison between homogeneous properties. The results of energy absorbed of the 3 samples are reported on the diagram on the right. The 50–50 shows the optimal energy, compression energy, 40–60 and 50–70 lower values. This is a comparison. The first, the 60–40 iron urea, the higher the absolute value obtained for 50–50 iron urea, the intermediate 60 and 30–70 on the last one. The higher the urea amount, the higher the porosity, the lower the weight, the lower the density of the foam. But the highest specific absorbed energy was found in 50–50 iron urea foam in combination with intermediate measured values of both stress and strain. So if we put a greater amount of urea, we have lower density of the foam, but in the comparison of the ratio energy density, the trend is demonstrated on the graphic on the right side of the slide. So the optimum is achieved with the 50–50 foam. In this table I report the main physical properties, and in the graph on the bottom we can see that red point, the higher the density, the lower the deformation strain, and vice versa for red points. While for the specific energy we have not a uniform trend, but we have a maximum value for the 50–50 foam black. In conclusion, the accurate evaluation of the mixture is fundamental for the prediction of iron foam's mechanical properties, compression. These are strongly dependent on the ratio iron-urea, and the compression tests have shown the optimal mechanical strength of the manufactured iron foams and their energy absorption ability. The porosity is strictly connected to the greater presence of urea, and just we look to the density, the 30–70 foam represents the best composition. If we look to overall performance in terms of energy absorbed and to the density, it's important to take into account also other properties that are energy absorption, deformation strain, plateau stress, and so on. And from this point of view, other solutions offer a good mix of physical and mechanical properties. In particular, 30, 40, 60 and 50–50 also must be considered. Thank you for your attention. If you have questions,